Okay, so this is part 2 of chapter 10, talking about experimental designs and validity. So there are kind of two main categories: independent groups designs and within groups designs. Independent groups are also known as between subjects or between groups, and within groups are also known as within subjects, and just groups of subjects. So here's an example of a between groups design known as a post-test only design. Okay, so you have, and this is a pretty simple experimental design, probably what seems most familiar, where you have two groups, and individuals are randomly assigned to group 1 or group 2, and then there's some intervention, and then the dependent variable is measured afterwards. Okay, so here's an example: randomly assigned to either take notes on a laptop or notes with a pen and paper, and then measure accuracy on a comprehension test afterwards. Okay. You could also have a pre-test, post-test design with two separate groups. Okay, so you have two measurements in this case, pre and post intervention. Okay, so here's an example where you have one group randomly assigned to a mindfulness class, one randomly assigned to a nutrition class, and then the dependent variable is really the improvement on a verbal GRE score. Okay, so they take that test twice, so you get both the pre-test and the post-test. Okay. Take it before, take the class, and then take it after and see how it changes. Okay. Let's see. So when would you use one of these versus the other? It really depends on the research question, the research situation. Sometimes it's not going to work to use a pre-test, post-test design. There's sometimes a novelty effect that you need to have in order to see the effect that you're interested in. Some things can't be unlearned, for example. Sometimes it does make sense, though. If you want to look for change over time, improvements, increases, decreases. If you want to control for between group variability as well, and individual variability, then they can be powerful. For example, if I show you this, you can see that the two bars are equal heights. Okay, so you can verify that the groups were the same prior to taking the class. So you didn't just have a really good group that happened to be randomly assigned to the mindfulness class versus the nutrition class. They were equal prior to the intervention. Okay. You can still answer plenty of questions with post-test only designs. They can still establish causation. But you might just have to make sure that the groups are equivalent or matching or other things like that you don't get. So within groups designs, let's talk about those. Here's an example of a repeated measures design. Okay, so within groups designs, what really defines them is that participants are exposed to all levels of the IV, but at multiple different times. Okay, it could be 2 or it could be more. So here's an example of a group. There's just one group of participants, but they're measured twice. One measured twice. Once they taste chocolate with another person tasting chocolate at the same time. The other time they're tasting chocolate just by themselves, and then the ratings after the tastings are the dependent variable. Okay. A concurrent measures design is where you have participants are exposed to all levels of the IV at roughly the same time, and then the dependent variable is going to be some kind of a preference. Okay. So this could be taking one group. Here's an example of babies. Okay, they're put in a room and they have two pictures, one of a female face and one of a male face, and then they measure the looking preference, how often they tend to direct their gaze towards one face or the other. One great thing about within groups designs is that there's just one group, so you don't have to worry about the potential for group differences that randomly came about through random assignment. Everybody serves as their own control. And you can save some money. You don't need to compensate as many participants. In fact, it's about half. Okay. Some things you need to be careful of, though, are order effects. Okay, so in this chocolate tasting study, you're going to, if you had everybody taste chocolate alone first, and then, or taste chocolate first with somebody else eating chocolate with them, and then taste chocolate alone. And the idea of this experiment was to see if having a shared experience with somebody else would enhance the experience of tasting the chocolate. Then there would be a confound there, because if there are higher ratings for the first condition in which they were tasting chocolate with a confederate, then that could also just be due to that was the first time they got chocolate that day, and the first bite of chocolate always tastes best, right? You have kind of a diminishing returns as you eat more chocolate. Okay. And so you can avoid those order effects by counterbalancing. So in this case, the participants are randomly assigned an order. Some of the participants tasted chocolate alone first and then tasted chocolate with another person second. Others, it was the opposite. Okay. So order effects, that's when being exposed to one condition affects how participants respond later. Sometimes this takes the form of practice effects, where people just get bored with a task. Maybe they figure it out and improve. Their performance improves. So counterbalancing, though, is going to help to take care of that. So any practice effects that are observed, they're going to be randomly dispersed, haphazardly dispersed between the two conditions. Okay. Carryover effects, that's where you could have not necessarily practice, but just some kind of contamination from early to later. Okay. So maybe you have like a lingering taste in your mouth. So maybe you're eating something disgusting and then you eat something good, but you might still have a little bit of disgusting taste in your mouth that could affect the good one. And so you wouldn't want to be assigned to that particular order condition. Full counterbalancing, that's where all possible condition orders are represented. So counterbalancing, that's just where order is randomly assigned, as I mentioned. If you have a bunch of conditions, then this can get tricky. You'd need a whole lot of participants to have all possible combinations represented. So sometimes there's just partial counterbalancing, where you just have computerized randomization, so maybe not all possible orders are represented, but they're at least random. And then a Latin square is where every condition ends up in every position. So here's an example of a Latin square. You can see 1, 2, 3, 4, 5, 6, and then you just kind of move this. Here's 1, 2, 3, 4, 5, 6, and then you just move the numbers around and move the rest down, so that it just gets spread throughout. So it's not exactly random, but it's at least evenly spread out. Okay? And participants, of course, would be randomly assigned to one of these rows. Okay? So some disadvantages, as we mentioned, there's the potential for order effects. Sometimes it's not possible to have a within groups design, because some things can't be unlearned. And sometimes experiencing all levels can change the way participants act. Okay, so if you have multiple exposures to something, if you're employing deception and you don't want participants to actually know what the purpose of the study is, if they're exposed to the same thing over and over again, they may start to get more suspicious, and that might kind of cause them to act differently. So that's what's called demand characteristics. Now you may wonder, this pre-test, post-test design that I mentioned before, is that a repeated measures design? Technically, no. You have so half of the participants got exposed to one level of the IV and the other half got exposed to the other one. With a true repeated measures design or within groups design, all levels of the independent variable need to be experienced by all participants. Okay, so that's the case with repeated measures and concurrent measures designs. Okay. Of course, you want to make sure that you interrogate all four validities: construct validity, how well do the IVs and DVs really capture the concept variables that you're interested in. Pressing a button on a toy that doesn't work, is that really an accurate measure of perseverance? Or does that truly capture that variable of perseverance? Sometimes you're not interested so much in like how well something captures something, but just to make sure the experiment is working correctly. So it's very common to do a pilot study. It's best practice to do a pilot study before doing a full experiment, where you just run your basic experiment on a small group of participants typically, and you just want to make sure that your experimental design is working, that there's not things that you haven't considered. Make sure the instruments are running properly, that they're running reliably. Just for proof of concept is what it's called, to make sure that your design works well. Okay. You'll see these in the literature sometimes. These are often still published, but it's published as a pilot study saying, hey, this isn't fully conclusive. We just kind of wanted to make sure that we could observe what we'd expect to observe here, that we'd see these effects of the DV on the DV of our IV. External validity, generalization. Generalizing to general population, generally not possible. That's a lot of generals in there. Usually experiments aren't really designed with external validity prioritized, just because you're really trying to prioritize internal validity, and for that you need to often create a very artificial and very controlled environment that isn't very representative of the real world. You also usually cannot expect a random sample, okay, to be able to generalize to the population. So external validity, usually don't get it until you've done multiple experiments, and you can see how a particular effect may generalize to other situations. And then you can recruit in different populations as well. Okay, statistical validity, asking questions like how much, how precise, what else is known. Cohen's d is a measure of effect size that you might come across when looking at experiments. That's showing the how big of a difference there are between two averages. So if you have two groups, you compute the average perseverance score between the two or whatever. You may find a significant difference, but it may be big or small, a big or small effect. So Cohen's d gives you a measure of effect size. Confidence intervals, of course, that gives you a measure of precision. And replication is necessary over time to see how big is the actual effect size over multiple studies. And does it actually hold up, or was this one study just kind of a statistical fluke? Internal validity, that's what we've talked about at length. Okay, the main thing is, are there alternative explanations for the results? Do we have all the proper controls in place, or are there any confounds that we need to consider? Okay, that's the end of this chapter.